Welcome to Part 3, where we will look at standards and fiber selection. Many international and national standards govern optical cable characteristics and measurement methods, but the two main groups that work on international standards are the IEC and the ITU. The IEC is a global organization that prepares and publishes international standards for all electrical, electronic, and related technologies which serve as a basis for national standardization. The IEC is composed of technical committees who prepare technical documents on specific subjects within the scope of an application in order to define the related standards. For example, the Technical Committee TC86 is dedicated to fiber optics, and its subcommittees focus on specific subjects such as SC86A for fibers and cables, SC86B for fiber optic interconnecting devices and passive components, and lastly SC86C for fiber optic systems and active devices. The ITU is an international organization that defines guidelines, technical characteristics, and specifications of telecommunication systems, networks, and services. It includes optical fiber performance and test and measurement applications and consists of three different sectors: radio communication, ITU-R, telecommunication standardization, ITU-T, and telecommunication development, ITU-D. The workhorse among installed fiber types is Category G652, the first edition being standardized in ITU-T in 1984 and developed over time to the most current subcategory G652D. This fiber category is by far the most widely installed globally. For several years, ITU-T G652 cabled fiber recommendation incorporated the C and L-band extensions with cabled attenuation attributes at 1625 nanometers, resulting in a wide transmission spectrum from 1260 to 1625 nanometers. This wide optical spectrum is used in optical telecommunication, terrestrial long-distance, submarine, metro, CATV, and FTTx networks. Similar fiber types have also been standardized by the IEC. IEC SC86A not only standardized bare fiber types 60793-2-50 series, but also developed a full scale of cable types, indoor, outdoor, aerial, and microduct cable, serving an extensive range of applications, 60794 series of standards. In addition, IEC developed a wide variety of testing methods for cable types, acting globally as the main cable test methods. The other commonly used fiber types used in telecom networks are G653 zero dispersion shifted fiber, optimized for the 1550 nanometer window; G655 non-zero dispersion shifted fiber, optimized for the 1530 to 1620 nanometer window; and G657 bend insensitive fiber, which we will discuss in more detail in the following section. As discussed earlier, macro-bending loss is caused when the fiber is under constant bend radius. An optical signal traveling through the fiber core can lose a fraction of its power in a bent fiber, as the tighter the bend radius, the more optical power is lost. Macro-bending loss in single-mode fibers is characterized by a relatively strong increase in loss above a certain wavelength. Micro-bending loss, though, is caused by longitudinal perturbations of the fiber, usually related to intense contact of cable materials to the optical fiber, for example, shrinking effects in tight buffered cables or less optimized loose tube cable designs. Micro-bending loss usually shows less wavelength dependency compared to macro-bending loss. Particularly in older cable types, increased loss could be present at higher wavelengths due to macro and/or micro-bending effects, in particular at 1625 nanometers and certainly at 1650 nanometers for monitoring applications. In order to overcome such bending effects, a category of bend-improved single-mode fibers was standardized by ITU as G657 fibers. 4 classes of fiber are defined in the latest ITU-T G657. G657A1, these are G652D fibers with an optically specified bending radius of 10 millimeters. G657A2. These are G652D fibers with an optically specified bending radius of 7.5 millimeters. G657B2. These are not compliant to G652D with optically specified bending radius of 7.5 millimeters. G657B3. These are not compliant to G652D with optically specified bending radius of 5 millimeters. Of these fibers, subcategory G657A2 fibers offer the lowest bend losses, both macro as well as micro bending, while still being fully compatible with G652D fibers. These fibers can be used for a wide range of demanding applications and cabling structures, from access networks to fiber-to-the antenna cables. A very special application for G657 fiber cable is high optical power distribution, for example for central office patch cords used for Raman gain applications, extensive DWDM or high-power video overlay. Light stripped off from the fiber core under fiber bending will be absorbed in the coating. At higher powers, this may lead to overheating of the coating, and in extreme situations to catastrophic failures of the coating resulting in fiber breakage, or even worse within a central office, fire. G657A2 fibers offer the best bending immunity for such applications. Such G657A2 fibers can also quite easily be used with reduced coating protection, for example, 200 micron coating diameter. Reducing the coating diameter usually increases the fiber sensitivity for microbending. However, in 200 micron coated G657A2 fibers, the microbending sensitivity is still acceptable, comparable to that for 250 micron coated G652D fiber, offering the interesting possibility of strongly reducing cable diameters, especially for high fiber count cables and microduct cable. Networks are built to last for decades, and they need to support without interruption or failure increasingly heavy traffic at higher bandwidths. Factors that contribute to the network's reliability and longevity, such as the need for good fiber and cable management and highly reliable connections throughout the network, have been accepted as necessary. In addition to meeting today's needs, operators need to build networks with an eye to future requirements. These have long been standard considerations for long-haul, core, and metro networks. What happens when FTTx fiber access networks are built? New standards and new technologies in the development of fiber optic cabling and connectivity directly impact operators' network considerations. Single-mode optical fibers are designed to operate with wavelengths ranging from 1260 up to 1650 nanometers. Below 1260 nanometers, the fiber behaves as a multimode fiber, while above 1675 nanometers, the fiberglass material starts to absorb the light. The graphic shows again a typical attenuation curve. Note that bends in the fiber cause an attenuation increase at longer wavelengths above 1550 nanometers. As shown in this graphic, standard ITU-T G652D fiber will typically show the wavelength-dependent attenuation increase when making 10 turns on fiber with a certain diameter. The graph indicates that a minimum bend radius of 20 millimeters can be accepted for ITU-T G652D fibers. However, when installing fiber in most connectivity housings, this minimum installation radius is not at all practical. ITU-T G657 bend-insensitive fibers were introduced as a solution. For G657A2 fibers stored with a bend radius of 10 millimeters, the macro bending loss is about 10 to 20 times lower than that of G652D fibers with the same bend radius. Also note that for the same fiber with the same bend radius, the bend loss at 1625 nanometers will be about 2 to 2.5 times higher than that at 1550 nanometers. When ITU-T G657 bend-insensitive fibers were introduced in FTTH rollouts, attention to installation quality and management of fibers and cables seemed to disappear. At the time, it was assumed that using bend-insensitive fibers in FTTH PON architectures using wavelengths up to 1550 nanometers maximum meant that relaxed patch cord specifications and less fiber management were permissible. Having looser specifications allowed operators to employ crews with lower technical skills in building out their FTTH network. Access and FTTH networks are very large, and training the vast number of people required to build them is time-consuming and costly. To reduce costs, to save time and meet commitments to various stakeholders, and to match the realities of the competitive landscape, operators have employed installation crews with limited fiber handling skills. Less skilled crews, however, mean even greater attention must be given to selection of materials and to network architecture. For example, proper fiber splicing requires skill, training, and experience, and fully trained splice technicians are expensive and increasingly rare. A network architecture that minimizes the number of splice locations, concentrating them and increasing their individual splice density, can help reduce costs but must be planned in from the beginning of the network's design. On top of that, many FTTH network business cases were calculated to have payback in shorter time frames and focused primarily on initial costs. This resulted in reduced specifications at 1310 and 1550 nanometers only of optical fiber cables and connectors, and reduced attention to installation practices, for example, uncontrolled bends in stored fibers. This trend can soon become a costly issue since the current networks might not be able to deal with systems operating at wavelengths above 1550 nanometers. Should network deployment decisions be based on financial CapEx calculations without considering the long-term effects of these decisions and ignoring related OpEx costs? It is tempting to implement savings on the quality of material used, on training installation crews and assuring that specifications meet the real needs, although the relative cost for this quality is typically a very small part of the network's complete total cost of ownership. We should remember that the initial CapEx of an FTTH deployment consists mainly of civil costs, about 70%. Cost of actives, about 23%, and civil hardware, cables, connectors, closures, distribution frames, about 7%. So the passive equipment, which in general sees long service lives, sometimes in the harshest conditions, is a relatively small cost of the overall installation. However, their impact on later OpEx, due to the costs involved in replacing them, can be huge. OpEx costs, assumed to be around 15% of CapEx but occurring annually, impact the network business case only later on, and for that reason seem to be ignored during fiber access FTTH network builds. Let's consider how use of G657 bend-insensitive fibers impact CapEx and OpEx. Although optical performance of macro bending improved greatly, the fiber's mechanical reliability remained the same as for G652D fibers. By allowing smaller bend radii, the probability of mechanical failure also increases without an optical attenuation warning. In the ITU-T G657 specification, a failure probability of 10 to the minus 5 is considered acceptable for FTTH applications. For long-haul networks, a much lower failure probability is requested, as one failure could affect the transmission of several thousand customers. As shown in the figure, the expected reliability of the fiber lines depends on the type of network. In core, metro, and long-haul fiber networks, attention has traditionally been paid to the deployed network's long-term reliability. Networks have been built to last for decades and have had to support without interruption or failure increasingly heavy traffic and higher bandwidths. Reduced network quality inevitably leads to increased downtimes. Downtime affecting residential customers was historically not the highest priority for network operators. But times and customer expectations have changed. One network operator executive described the change of customer contacts at downtimes as an increasing drama effect. Customer calls are much more emotional than in the past, as people are almost continuously online. Fortunately, as pressure and expectations from both business and residential customers has increased, technology has evolved. In recent years, standards and technologies have opened a wider portion of the fiber spectrum to assure that expensively deployed networks are built to last. The NG-PON2 transmission standards at ITU-T allow operators to increase the FTTx network's bandwidth capacities and reduce deployment cost by sharing the same fiber with more connected customers or sharing networks with multiple operators. These standards, using transmission wavelengths from 1260 to 1625 nanometers, employ more of the same fiber deployed and allow seamless overlays of new services to existing GPON networks. The NG-PON2 downstream channels will operate in the wavelength band between 1600 and 1625 nanometers, which are the transmission wavelengths most sensitive for bending of the fiber. Surprisingly enough, the current ITU-T and IEC performance standards for cables and connectors do not always reflect the requirements for these future transmission wavelengths. For future-proof networks, all network components should be specified for use at 1625 nanometers. Standardization bodies like ITU-T and IEC will pay attention to this in the revisions of the standards for cables and connectors. In the past, operators replaced connectivity components in the core network when they started to use longer wavelengths in order to increase the capacity of their fiber builds. For FTTx networks, the impact of such rework would obviously be multiplied, as the number of connectivity points is huge compared to those in the core network. Looking at the fiber loss, a fiber incorporating a tight bend, the downstream signal can obtain significant losses up to 1 dB, which obviously can affect transmission to the connected customers. Imagine upgrading a network to connect customers with an even higher bandwidth, and suddenly the service phone rings at the operator's service center. This chart illustrates the performance of the G657A2 bend-insensitive fiber compared to the standard G652D fiber. As pressure and expectations from both business and residential customers has increased, technology has to evolve. In recent years, standards and technologies have opened a wider portion of the fiber transmission spectrum to assure that expensively deployed networks are built to last, even when new transmission equipment or systems are added to the line. Factors that contribute to reliability and longevity, such as the need for reliable connections and good fiber and cable management systems throughout the network, are necessary. To survive and grow, operators need to build networks with an eye to future requirements. Change will happen, that is certain. What form the change will take is less clear, but future use of wavelengths up to 1625 nanometers is a certainty. Lessons from the past: training crews to handle fiber properly, using solutions supporting correct cable management, using connectors with the right performance specification, provide both short and long-term benefits to operators and customers alike. That completes Part 3. Please continue on to Part 4. Thank you.